Good afternoon, ladies and gentlemen. Before I start, because I'm Welsh and it's the St. David's Day today, the patron saint of Wales, I have to say Dydd Gwyl Dwy Hapus, which is Happy St. David's Day. Thank you, Roger. We are looking forward to a talk today by Glen, who's a new member of staff here, and we welcome him. And he did his undergraduate degree in UJ, because he's a Joburg boy, so he's local. And then he did his MSc in UCT, and he went to work for Sibania for 9.5 years, and then went to Würzburg in Germany to do his PhD with Hartwig Frimmel, which he was awarded last year, cum laude. And he also won the South African Rising Star Award in 2014. So I think we're delighted that he's joined us here at Wits. So Glen, your first Geotalk.
Good afternoon, everyone. I hope this is not too loud. The talk that I'm going to be presenting here is work that I started doing with Hartwig Frimmel. It's part of the sections that form part of my PhD, which we started in 2014, but I was not a registered student by then. I was just interested in looking at something in the vets while I was working in the mines. And the first thing that I looked at was actually the shales that are very close to what we call the carbon leather, one of the reefs that has been exploited extensively in the Carltonville area. And with this, I started noticing some anomalies in gold concentrations on the shales actually that are just below the carbon leather, and these are the Rutherford Formation shales. So, I will be talking mainly today about highly stereophyte elements, and in this context I will actually be referring mainly to gold and PGEs. For many years gold has actually been used as a metal that has been used to measure wealth in different countries, and there has been one person also in Mali called Mansa Musa, who is actually maybe it's Musa who came back again, but this Mansa Musa was actually one of the richest human beings who have ever lived. By the time he died, he had over 400 billion US dollars equivalent of today's money, and the only wealth that he had actually was mainly gold. So gold became noble things for over 6,000 years in many places where they have started mining it. But the surprising it is in the upper continental crust or in the continental crust, highly stereophyte elements occur in extremely very low concentrations. As you can see here in the crust itself, we only have about 1.5 parts per billion of gold. For platinum and palladium it's even worse, because we have concentration as low as 0.5. And all these metals that I'll be talking about, they have a Clark value about 10 to the power 3 to 10 to the power 4. But another opportunity is that in chondrites, we do have elevated concentration in a ppb scale also, up to 148 parts per billion for gold. And the PGEs appears to be doing much better than gold in that particular scale. But based on the latest calculations, we know that we have over 45 billion tons of gold that is actually finely dispersed into the crust itself. So where is all this gold? Is it only concentrated now in the deposits that we know of? And where are these PGEs? Are they only located in the Bushveld complex in the context of South Africa? So now this initiated some of the things that we have been working on, but the first thing it was to find out which best rock type represent the upper continental crust and which rock type can be used to actually trace the signatures or the background concentration of highly stereophyte elements. And I found that the marine shales, whether coming from the Wits or from the Transvaal supergroup or coming from all the sequences, are some of the best reliable proxies for the general lithological makeup of any hinterland at a given time. So, why the Kaapvaal craton? Because there are other cratons where we also have shales and all that, but the Kaapvaal craton offers a very unique example of best preserved records of marine sedimentation, including fluvial sedimentation. But on top of that, we know that we are one of the richest people in terms of mineral wealth, where we have a major gold province in the Witwatersrand Basin, and we also have large PGE deposits in the Bushveld and large iron ore deposits in the Transvaal Basin. So the objective of this particular talk actually is to use sediment provenance and some mineralogy in order to estimate the background concentration of highly stereophile elements in Archaean and Proterozoic marine shales. And this actually can also serve as an indicator or a signal of how much gold was actually in the oceans at those particular time. So in order to fulfill the objective of this study, 3 main sequences that are very prominent and only regionally persistent shales were actually sampled. Started from one of the oldest sequences that we have, the Barberton supergroup, where we took samples from the fig tree and the modest group. Although you must keep in mind that there's only limited exposures or samples of marine shales in the Barberton, so we had to be very selective. But at least we had people helping us, such as Axel Hoffman, who also gave us some of the samples. And then in the Wits, we sampled all the gold fields, started where I was working. I started in the Carltonville gold field, and then we went to the Free State, Klerksdorp, East Rand, and the Evander gold fields. And in the Transvaal, the only good prominent samples were actually sampled in the South Deep side, where they had a project there, so we managed to get 2 drill cores from there. So fortunately enough, we also got the Black Reef, so we got the Pretoria group for the Transvaal, and we also have the Black Reef shales. So the question is, if we do find that there is some siderophile elements in these shales, what do they exactly represent? Do they actually represent a particular sediment provenance, meaning that if you have excessive granites as your basement, are they affiliated with the highly siderophile elements that we find in shales? Or they represent the seawater chemistry of that particular time, meaning that there was some sort of an effective trapping mechanism at those particular times that has concentrated gold and PGEs in these particular shales? Or they actually represent what others have called a huge influx of gold and PGEs in the Archaean land surface. So some of these questions will be answered during the course of this talk. So in order to do this, we selected samples that are not mineralized. Mineralized, I'm referring to pyrite mineralization and other sulfides. So we were very specific with this. And we took about 33 samples from the Transvaal supergroup and more samples from the Wits, and a few of them in the Barberton. And the methods that we actually use are actually typical methods that are usually used in geochemistry. The only thing that was different was the tools that we have used to measure for ultra low concentration of gold and PGEs. So we tried a couple of methods, but if you're interested in one of the methods that we have used is by Ian Pitcairn, where they discovered new method to actually analyze extremely low concentration of gold. Because previously people used to use neutron activation, and they also used to use fire assays, but the detection limits were very high. So at least now we can use aqua regia digestion methods that can actually assist us to go far below the ppb scale. So the first thing that was done was to screen these shales mineralogically to see what are they composed of. And I'll just give an example here with the marine shales of the Witwatersrand, looking at the Central Rand Basin and the West Rand Basin. And what we found was most of these shales are actually rich in chloride, mainly iron-rich chloride, as you can see with the colors green. But another feature that we actually found that we're not expecting to find is the amount of carbonates that are actually in this shale. As you can see with the calcite, the white spots that are indicated in here. So with this, we decided to select those which can best represent the composition without any major alterations. But we also took some of the altered shales to actually see what they have. So to see what grade of metamorphism actually these shales were actually subjected to, we look at the mineralogical assemblage, and we looked at critical minerals, and we realized that this is similar to some of the things that other people have found, such as Bradley Guy and Bertha Smith, who is sitting here, and other people who have actually worked in the shales of the Wits. And then from this, we selected about 129 chloride grains from these different shales, so that we can see at what temperatures of formation were they actually subjected to. And I did, I used an electron microprobe, then I screened out to make sure that the samples that I'm looking for are actually chlorides. And as you can see, all of them are clustered in one particular block. Then from this state, it was to petrologically screen the differences between hydrothermal chlorides and metamorphic chlorides. And with this, I relied on the texture and how they look and what are they affiliated with. And from distinguishing the difference between metamorphic and hydrothermal chlorides, I actually look at the iron and magnesium ratio to see if they are completely different and to see if these are actually two different types of chlorides. But all of them appears, we found them to be actually iron-rich chlorides. And then from this, I used about 11 geothermometers to actually calculate the temperatures of formation. And before doing that, I had to make sure that there's also sufficient aluminium-bearing minerals to make sure that we have full Al saturations for us to be able to estimate the temperature. And as you can see, these estimates are not too far out from what guys such as Neil Phillips and Hartwig Friemel and others who have actually worked in the Wits have actually found. So these has actually have some significance, but I'll come to that later. We look at the trace elements composition to see if there's anything unique. I have normalized these shales actually using post-Archaean Australian shale, but at the same time I also use some of all the rocks that may be representative of the source materials such as basalts and all that to see if we do have spikes in something else, in some of them. But one thing that stood out was all the Archaean shales are actually having different chemical composition when you compare to Palaeoproterozoic shales, especially the Pretoria group shales. And this you will see soon in the next slide. So the next thing that we did was actually to look at the background concentration of gold and PGEs. Actually, we analyzed about 6 different types of PGEs, but here I'll only present platinum and palladium. And with this, we found that there's not huge variation starting with the younger ones, the Transvaal and the Black Reef. But one thing that stood out on the Black Reef was the high amount of PGEs, but not only the PGEs, there was also high content of manganese on the Black Reef side, and other base metals that I did not include on this. But if you look at the Transvaal, you'll see that all the gold and PGEs are mainly below a line of 5 ppb, ranging between 1 to 4 ppb, most of them, with few spikes. And those spikes actually that we have observed there were in portion where we had shale and siltstone intercalation, meaning that we have a bit of coarser sediments. And then looking at the Wits, starting with the Roodepoort Formation, which represent the uppermost part of the Western Basin. And here we found many things. We also found large anomalies, or a lot of anomalies, especially on gold. But the PGE content was actually very consistent. As you can see, there's very much less variations. And then the Boison's Formation was the one which represent the only marine unit in the Central Rand Basin, had a lot of gold compared to the Central Rand Basin marine shales. And with this, we did a lot of work on the Boisons just to make sure that this is not an analytical error and all that. And I will present some of the samples from the Boisons Formation, and I'll also present some from the Roodepoort Formation, trying to link the story with the chlorides. Then looking at the Barberton shales, these ones also were very highly variable, meaning that it was not even easy to get the statistical mean of them or an average for them, especially the ones from the Fig Tree group, and then the Moody's group were actually relatively constant. So in order to get the average before we get to the interpretation of the data, we tried many methods. So the first thing was to calculate a simple arithmetic mean to make sure that this actually comes out well, and to plot this in a histogram. And we found that most of our analysis, especially the ones from the Wits, are actually either forming a positively skewed or a negatively skewed, what we commonly refer to in the industry as log normal distribution. And from this, we tried various data transformation methods. The first one was the Archaean transformation method, and we realized that this does not actually correct the mean, and it's not easy to get to treat the outliers. But what worked better was actually a log normal distribution, where we added a standard a third parameter that assisted us to normalize the data without ignoring all the anomalies or the outliers. And this actually helped us to get the two types of mean. So we actually had the arithmetic mean, and we have what we call the estimation mean, which is based on the log normal transformation. And you will notice that sometimes they differ. And in some of the samples, you'll find that the difference is over 5 parts per billion. So we realized that the log normal distribution type of method for summing up this data was the one that was working much better. So now to give some averages before we go ahead to the interpretation, you will notice here that in the Barberton shales, we do have high peaks of gold, as you can see actually in this graph here, representing the fig tree and the Moody's group. And then the largest peaks that we have as an average is actually sitting in the Wits type of shale, and mainly the Boisens shale, but the Rudderport formation also do have a high gold content. And I also plotted two formations of two different gold fields of the Boisens for illustration purposes. So I plotted one from the Western Area formation, which is represented by this peak, and I plotted one from the Welcome gold field, which is represented by that peak. And then you will notice that the Black Reef also have sufficient amount of gold, even higher than some of the Moody's shale. But the Pretoria group shales have nearly one of the lowest gold content. You can compare that with some of the Moody's shale. But when you look at the PGE content, you will notice that the Wits are again the same type of formation at a particular time. And what you can do is you can actually draw some sort of a line here where you will notice that the peak is around this particular period, and it actually goes down going this way. So what exactly was happening during that particular time? Why do we have so much gold in unmineralized shales, in carbon poor shales? When I say carbon poor, their carbon content is actually less than 0.548%. So the first thing was to check the spikes that we have in the Wits shales. Are they representative of any type of alteration and all that? So for this, we actually took a very nice profile from the Rudderport formation. And with this, at least here, we could observe both non-altered shales that I refer to here as pristine shale. And then we had a lot of seritization in those particular shales. And then on the top part of it, before we actually reach the main formation, which above it, on it, we have the carbon leather. That's where we had a lot of chloritization. But one thing that you must notice is the scale of this alteration, that it does not extend to over a meter. It's actually around 0.8 meters. So I used Grayson's equation to actually see if there was any metasomatism on this, meaning the change in any of the concentration of this or movement of these elements, or it was actually an isochemical type of alteration. And looking at this, you can notice here that as much as there is alteration or deviation from the isocon line, one thing that stands out, all these elements are within less than 10% of their concentration change, meaning that even those that are chloritized or that have been affected by seritization and the least pristine shales, their gold content actually is not really controlled by a lot of post-depositional alteration. Although chloritization, as you can see in the next slide, did play a particular role, because if you can see in here, you will notice that we have the highest peaks close to 100 parts per billion, where we have chloritization, but in the pristine shales, we also still have something that is approaching about 50 parts per billion. And this is actually not the first time something like this was observed. In 1987, Phillips actually published a communication where he reported anomalous gold content in the Wits, which actually led to a series of publications to say that maybe some of the gold that we have in the Wits may have been sourced from these shales, because the concentrations that he got there were actually excessively high. And then now looking at the sediment provenance, where are these shales coming from? Which source rocks actually were actually responsible for the Archaean hinterland or the Palaeoproterozoic hinterland? So in order to fulfill this exercise, the first thing that I have done, I took a couple of elements and actually look at their ratios to see if they have changed. So I took elements that are actually prone to fractionation, such as chromium, and I also took nickel and actually measured their ratios from the Barberton shales and compare it with the Wits shales and also compare it with some of the Proterozoic shales. And I realized that from the Barberton shales and the Wits shales, the ratio of chromium and nickel is actually relatively similar, but it differs as soon as you go to the Pretoria group, which is more of Palaeoproterozoic. And then from this, I use a typical basalt, and I use a typical granite, and I use a typical TTG, and an andesite, to actually use them as a reference samples. So I plotted everyone's data who has ever published something, and I have actually used these cycles to indicate actually the classes of different source rocks. And as you can notice here, all these samples are scattered around. For an example, some of the Barberton shales indicate that they were sourced from a more mafic dominated source. But the other thing that you can notice, look at the two Boysen's shale formation. I will actually use just the legend here. In the Welkom goldfield, you can see that the source was mainly felsic, and you can see all those shales are nearly plotting very close to the felsic source, which is actually just in this portion. Whereas you look at, again, at the same Boysen formation in the western area side, I realized that the source there was mafic, meaning that the source actually was not consistent throughout the basin as much as we do have regionally persistent shales. But in all these shales, one thing that stood out based on these references, it shows that the hinterland was mainly an Archaean Proterozoic granitoid greenstone terrain. But what does this have to do with the gold? But before we can do that, just look at another example from three different goldfields, looking at the Welkom goldfield, Klerksdorp goldfield, and also looking at the central and the eastern goldfield. You will notice that there's high variability in terms of these shales, irregardless of the similar formation or different formations. But all of them still indicate that the source was more of a granitoid and a greenstone. And then another observation that we have noticed that within a particular sequence that we thought is more felsic, by again using elemental ratios, we notice that there is in the Boysen's formation, the Klerksdorp side, if you can look at the depth that is indicated here, with the top elements here indicating both mafic and felsic end members, you will notice that in between, it appears that there was a change in the source or the hinterland itself, because we start here with a different composition, but somewhere in between something changes. But the other thing that you can notice from this diagram was the intensity of chemical weathering regardless of the source, which is indicated by these particular points that are in here. And to correlate gold, for an example, with other elements to see if we can find something that shows that gold is actually affiliated with something, we actually used different elements. The first one was more of mafic representative, and then we also have uranium and total organic carbon here, and then total sulfur on the other side. But you'll notice most of the samples are not correlating with both organic carbon and sulfur, although there are some of the spikes, as you can notice at your right on the sulfur side, that shows that there is some correlation with few samples, but majority of the samples are not showing any good correlation between carbon. And this is actually something that leaves question mark, because most of the time gold in shale or in marine shales is usually associated with organic matter. And then looking at the weathering patterns, I use different schemes, but for here I will only present two of them, the chemical index of alteration and index of compositional variability. You will notice that all these shales, mainly the Archaean ones, but also if you look at the younger ones on the Transvaal side, they were subjected to intensively high source area chemical weathering. And the other thing is the Wits shales, which are indicated by the graph on your right. You will see that they were actually sourced from a complex or a highly variable source, because they are plotting in a scattered position, and as you can see with the ICV number, typically you'll expect an ICV number of between 1 and 2 or 0 and 1, but with this you see a span starting from 0 up to greater than 3, showing that the source was actually very complex. But now, we have spoken about the sediment provenance. We understand these are actually coming from an Archaean basement, a granitoid, which many people have studied on them. But looking at the case of the conglomerate, which everyone has worked on, we understand few things, or many things now, by the Archaean environments. The first thing we know that it was in the Meso-Archaean, we actually had a large amount of CO2 degassing caused by volcanic activity, and it was mainly reducing atmosphere, meaning that the intense chemical weathering that we observe in this shale is actually justified. But this also indicates that the solubility of gold was actually very high. So provided that we did have some gold in these basement rocks and all that, it means we could dissolve a lot of gold, and we had a large influx of gold across the Archaean land surface. And there has been different models that have been proposed to say that, the latest one being Christoph Hendrich, where he said volcanism and microorganisms are responsible for the precipitation of gold. And we have Hartwig Friemel also, who's saying that the precipitation of gold was actually governed by oxidizing microbes and all that. But still, this does not really answer the question of the gold that we have in the conglomerate. Is it related to the shale? Because firstly, if we're speaking about microbial colonies, we don't have a lot of microbial colonies in the deep marine environment. And with this, at least in the coastal side or shallow marine side, we can actually precipitate gold either by oxidation, as Friemel has suggested in 2014, and other people before him, or by reduction, as Hendrich has provided in his 2015 Nature publication. But still, this does not explain the elevated gold content in the shale. The other thing that I have showed was the lack of correlation between sulfur and some of these highly siderophile elements, or sulfur and organic matter. Of course, some people will also make a case to say that most of the organic carbon, that's why we have less organic carbon, it was actually used up during the formation of diagenetic pyrite, and that's why we actually have less amount of carbon into this, and that's why we don't have correlations. And as I have explained, we don't have microbial activity in the deep ocean, or at least by our understanding by now. So this actually calls for a gold concentration process that is not only dependent on microbial activity, but it requires something else. So I will use 2 or 3 slides before I conclude to take you through the journey of our proposal, to say that these are the most probable sources why we do have this elevated gold concentration in the shales. So the first one that we propose, which has actually been proposed by other people in other things, we know that in the Wits, for an example, we have a lot of pyrite, and pyrite has been studied by many people. People from here at Wits University, UJ, Axel Hoffman is basing most of his research in the Archaean pyrites, and other people have also studied the pyrites. And all of them came to the same conclusion, to say that most of the sedimentary pyrites and diagenetic pyrites are actually rich in gold, and you can actually get gold as high as 197 parts per million. But now, if we look at unmineralized shales and we try to calculate, to do a simple mass balance, we actually have less than 3 volume percentage of pyrite in these particular shales, because they are pyrite poor. And if you use an average that was provided by Roslage, I have provided an article there, Gold in the Ocean Through Time, which is 90 ppb, but Roslage actually use coarse grain pyrites, and guys such as Andre use fine grain pyrites, where they found that you can even find 1,000 ppb in this shale. It can only give us between 2 and 4 parts per billion concentration in these shales. So which process is accountable now for the missing amount of gold and PGEs in this particular shale? So for this, we did a couple of other things. Amongst it was to separate some of the pyrites, not only in shales, but in conglomerates, working with other people. And we did some experiments and we actually noticed something. So the first thing that we discovered while we were actually looking at this particular, at these different shades, we noticed that we also have PGEs that are actually hosted by nuggets of osmium and ruthenium in the vats. And this is very common in the eventicide. And I did some scattered electron microscope images, as you can see in here, of osmium and ruthenium. And we found that we do have some micro nuggets of PGEs, and we use an X-ray CT to see if we do find any particulate gold and all that. Of course, it's in shale, so it means we couldn't see much of the gold in unmineralized one, but we could see gold in the mineralized one. And then with the work that we're actually doing, we came with something to say that let's try to correlate, use element ratio and gold and see if we do find some sort of a linear regression. And with this, we use elements that represent the felsic component and the mafic component, plotting it with gold. And as you can see there, those zirconium representing more of the felsic component of it, and the mafic component represented by nickel in this particular case. And in both of them, there was actually a very good correlation, a negative correlation, showing a nice regression in the few samples that we did. So we actually came with a process that we tested with some of the things that for now, on a high level note, because we still have to publish some of these results, we can refer to it as mechanical coagulation and aggregation of sediments, where we infer to say that most of this gold was actually sourced in a particulate form, as much as there was some of the gold that was infused or included or absorbed into the pyrite during its formation in the deep marine environment. But you must also know that the formation of pyrite in such particular environment is limited by the availability of the tetraethyl ion particles and also the amount of organic matter that is available for a reaction. So with this process that we're actually proposing, we say that the predominant fluid that was actually present at a particular time, we know it was in a form of meteoric precipitation and oceanic water. And one thing that we have seen, the picture that you see on the side here, just need to mark it. The picture that you see in here is actually mud and some gold in it. So the shiny stuff, I'm not sure if they're visible, this is gold. So we did a couple of things to actually monitor and to see if gold actually can be concentrated in particular layers and all that, using simple things such as Stokes' law, and also to see if particles themselves can actually bond together to absorb some of the gold. And on top of this, we use other things that actually exist to say that yes, there was actually two predominant concentration mechanisms. The first one, as I have mentioned, was more on the pyrite side, but the second one, it means the oceans are not the ones that homogenized the gold. So it means the gold was actually sourced from the hinterland, irrespective of a specific rock type, but there was a specific process that was very active, which actually resulted in the absorption of gold in addition of the organic matter in a superficial environment or coastal areas instead of the deep ocean itself. And the subsequent sinking of these sediments that actually contain gold was actually facilitated by either the friction between the bonded particles that actually have gold, or the changes in the particle fluid density and chemistry itself. Because in some of the shales, you'll actually notice that, such as the Transvaal shale, if the same process was operating in the Palaeoproterozoic, why don't we have the same amount of gold in those shales? So this actually also indicates that there was a particular period within the Meso-Archaean, for an example, as indicated by those graphs, where we had elevated gold in the hinterland that may have been available for sourcing. But this is not only limited to the vats, because we also have it in the Barberton side. But this also implies that by the time of deposition of sediments such as the Pretoria group and all that, it means wherever the source was coming from, there was insufficient amount of gold to be recycled. And if you can check in the context of South Africa, we don't even have a single gold deposit affiliated with that particular time, because the only youngest deposit that we still enjoy the benefits of it now is actually the Black Reef, which is actually far older than the Pretoria group. And then with this, there are some conclusions. So the first one, as you have noticed that many people have drawn into this, we have noticed that yes, it is indeed that the source of these sediments was in Archaean granitoid and greenstone terrain. And the second thing, we noticed that there was the Archaean shales actually have more gold than the younger ones referring to the Pretoria group, and it looks like there was a circular variation with a maximum peak in the Meso-Archaean. And the lack of correlation between gold and things such as organic matter and sulfur does indicate that there was a specific mechanism that was also responsible for concentrating in gold. And this is also observed clearly in different stratigraphic units where you actually have different sediment sources, where we have proposed the process being a mechanical process where some of the particulate gold particles were actually absorbed into the clays before sinking into the deep ocean. But with this, the main conclusion is that the peak in AU enrichment, for an example, is more equivalent or coeval, or it correlates with the maximum gold accumulation in the fluvial sedimentation, which has been recorded clearly in the coarse grain sediments of the Central Rand group. So now, having mentioned all this, we have noticed that very close to where we have very good high grades in the coarser sediments and all that, the shales themselves also have some sort of elevated background concentration of gold. So we have identified a couple of places where we say that maybe this does represent similar style of mineralization or similar hinterlands in other places to test whether this was only unique to the Kaapvaal and other cratons, or this was actually a global event coinciding with the time of around 2.9 or 2.8 billion years. So it means the next step of the project is try to sample some of the marine shales, if we can find some, in other cratons, and to actually monitor their gold and PGE values to see if background concentration of these highly stratified elements can be used as proxies for exploration or to target exploration site where we may have similar deposits. And with this, I just want to thank few people. The first one, my sponsors, the NRF and Sibanye Stillwater Limited. I want to thank all the people that went together camping in the Barberton and a couple of other places. And I also want to thank people who helped me with the sample prep, because we had samples of over 500 samples. So I had people helping me here in South Africa and the team in Germany, and all the people who have been advising in this project, such as Lawrence Minter and David Reed. And with that, I would like to say thank you.
Okay, we're trying to record these Geotalks onto YouTube, and so if you ask a question, could you speak up, please? And if they don't speak up, perhaps Glen could repeat part of the question in his answer. So do we have any questions?
Oh yes, I actually had a long discussion with Excel on that. Excel was actually looking at mafic volcanics, not shales, and he was actually saying that there was a lot of submarine alteration, meaning most of the Archaean rocks in the Barberton are highly silicified. And when they are silicified, the measured concentration of gold, and mainly gold because they were only looking at gold, indicate to them that there is extremely low concentration of gold. But the gold concentration that they have reported is something between 3 and 7 ppb, which means is the concentration that you can actually recover or weather from some of these. So we're actually looking at two different topics. He was looking at the source itself, being the hinterland itself, to say how much gold do we have there. And it's actually not the very first time something like that was done. I think in 1985 here in Economic Geology Research Unit, Meyer and Sega, I think they published background concentration of gold in granites and mafic rocks, of which they published results as high as 370 parts per billion. Although our argument with Excel was some of the results were actually representing altered sequences of granites, therefore they cannot be representative. But I think there was sufficient amount of gold in different rocks, not in one specific rock, that could be weathered to result in some of the concentration that we have.
Okay, Sharad.
I have a comment and a question. My comment is about the Barberton supergroup, as you call it. It's, as far as I know, because I've been teaching this for the last 20 years, it's the Swaziland supergroup, not the Barberton supergroup. Okay, that's just a comment. The question is really about, in terms of the sources for gold and PGEs, one of the things that you have not considered in your argument so far is whether meteorites could be a source. And I'm not talking of a Freeland type.
Yes.
Fact. I'm talking about the background of the flux of material. And we know that in the Archaean there was a much higher flux, both of impactors and obviously of meteorites in the world. And so my question is, what have you considered that, and have you tried to look into that possibility that this could be another source of elevated gold and PGEs in the Archaean compared to
truly so, yes, we have considered them. People who write this paper is people like Ray Durain. So my argument there, I have actually put a separate section in this particular paper, of which I'm willing to send it to you if you want to read more about it, where I say that there was a period during the early stages of the Earth, mainly in the Hadean and the Archaean, where we had late meteorite bombardment, of which these actually may have resulted in insufficient core mantle differentiation, and this can actually may have been the source of this elevated gold concentration. But the question also will arise to say that, was this only limited to one particular special position, meaning that which cratons also can actually represent that particular source? Was this only unique within this particular south side of the country? And the other thing that I have also considered there was actually the excessive temperatures, because we know that we actually had high temperatures with this, and we know that in high temperatures we cannot have high concentration of gold in the melt, but we can have high volume of gold being affiliated with the melt itself. So I have considered that as a good candidate actually, or potential of this elevated concentration of gold in PGEs. And on the Swaziland comment, before I forgot, yes, I'm aware of that. Roger also mentioned the same thing as that, and I will definitely change that.
He's being chauvinistic.
Is there any possibility that a variation in the amount of reworking within shale packages could result in some of the variations in geochemistry that you see? Also bearing in mind that the Wits has got a lot more shale in it compared to the Transvaal supergroup. Therefore, you're not going to have so much reworking in there. Ditto the Swaziland supergroup, so you're not going to get as much reworking in there. So, is there a possibility that variable amounts of reworking, excessive reworking in some of the shales and Wits could result in higher gold levels?
Yes, the shales that Neil Phillips has actually measured, but his observation was mainly very close to reefs, meaning that things that we already know that they're actually rich in gold. But his observation was mainly that there is a lot of shale siltstone intercalation, which can actually be a very good indicator to say that not only was there excessive reworking, but these coarser grain sediments in the form of siltstone may have actually resulted in additional gold that is being introduced there. But we didn't find this actually in these unmineralized shales, especially the ones that doesn't have any intercalations in them. The only thing they have is more of lamination and all that. So we couldn't find any evidence that we could present on that.
So my question relates to the difference in gold concentration in the conglomerates as opposed to the shales. And if we assume it's maybe, as you've mentioned, maybe a different process of accumulation, but could another hypothesis possibly be that the conglomerates acted as a better conduit for fluid flow that may have enriched any primary detrital gold mineralization, whereas shales would have been a poorer conduit for any enriching fluids?
Actually, a 2015 paper by Phillips and Powell, they proposed that, but it didn't work out quite well, because I mean, if we have to use the shale or saying that the source was exactly the same, the first thing is what was the contours of this for us to actually have high concentration where we have high permeability. And their justification was actually that we had secondary permeability developing that was mainly post-depositional, such as the Fredefort event or thermal metamorphism that was happening there. But on the shale themselves, the shales we know that were deposited in deep marine, whereas the conglomerates we know actually these coastal sediments and fluvial deposits. So it's completely different processes. Even if the source can be the same, but the processes will have to be different, because you need a high energy environment or a very good trap, such as a microbial organism that are going to precipitate your gold, which we don't find actually in the deep oceans, because in the deep ocean we actually find organic matter that was actually concentrated very close to the surface, and it depends also in its reactivity. And we know in the Archaean bottom waters we didn't have a lot of oxygen to actually accommodate for that in some of them.
Is there one more question? Apparently not. Okay, so thank you very much for a very, very interesting talk. We've been mining the Wits gold since 1886, and there still seems to be a lot of new things to discover. So thanks to those people who've come from outside, our brothers and sisters from UJ in particular, and thanks as ever to John Hancox from CCIC Coal for the drinks and chips. I don't have a Geotalk speaker for the next 2 weeks. I've got people for the end of March and through April, but if anybody's got a Geotalk loo that they would like to give, please see me in the not too distant future, and obviously the talks will be posted in various places and disseminated by Raylene, and I'll try and get the date right on the next poster. Only 2 people noticed, one the speaker and the other was Matt. So thank you very much, Glen, for a very professional talk. We enjoyed it a lot. Thank you.